Thank you very much for the invitation to present at this meeting on artificial intelligence in pediatric cardiac sciences, discussing the new frontier. I have no disclosures. The artificial intelligence revolution in healthcare is already entering the end of its first decade. It is important to note that this revolution is actually the third revival in the field of artificial intelligence. However, it is the first one to have substantial impact in healthcare, and this is due to three major factors. First, a wider availability of compute infrastructure, including computing cloud and programming tools. Second, there is an increase in the amount of clinical data that is digitized. And finally, a marginally better readiness of electronic health record system to use and deploy AI-based solutions. Now, most people in the audience will be familiar with the basics of AI, and I've heard of the common AI application used in healthcare, including prediction models created using machine learning, image analysis and signal processing through deep learning methods, and natural language processing with recurrent neural networks. However, today's talk will address emerging AI method, which now allows us to address new types of clinical questions. It is first important for the audience to understand that machine learning is not new. What you are seeing here is an article published in 1959 in the IBM Journal. This study reports the design and development of the first machine learning algorithm that could regularly beat an average human player at checkers. These early machine learning algorithms and many of the current algorithms can only address simple problems. For clarity, the methods might be complex, but the problem to be addressed must be formulated in a simple way. The problem here is that many biological and clinical systems are complex systems. Complex systems inherently have two major characteristics. First, their behavior is not dictated by a small number of influential features. And second, the system as a whole often behaves differently than the sum of its parts. Now think of the classic approach to biomedical research. The classic approach is reductionist in nature, which is antithetical to the study of complex systems. Many common machine learning methods similarly use a reductionist approach in defining problems and tasks. With this in mind, the next generation of insights from medical data will require embracing and study complex systems using new analytics methods that do not use data reduction. I will start by providing an example of how we can study complex systems using novel AI methods that were not available even a few years ago. What you will see in the next few slides are extracts from my doctoral dissertation from 7 years ago. In this study, we used a classic approach to complex systems to study the risk of thrombosis in pediatric patients undergoing cardiac surgery. We enrolled 398 patients who had a prevalence of postoperative thrombosis of 26% and collected data on 493 clinical risk factors. The first step in classic approach was to depict the system as best as you can using known biological association. What you are seeing here is a coagulation system overlaid with various clinical complications and component of cardiopulmonary bypass. The second step is to reduce the system to a set of binary associations. And in the final step, we extrapolated the system behavior in a theoretical but non-quantifiable framework. Now, while this exercise is not futile and can provide important biological and clinical information, it does not provide any actionable insights and cannot be used to individualize patient management. In recent years, we have revisited this data and used a method called clustering graph neural network to turn our original non-quantifiable framework into a fully quantified network that can be used to optimize and individualize patient management. The graph model includes clinical status, patient management, biomarker measurements, postoperative recovery, and various complications able to predict the likelihood of a specific outcome for new patients with a high degree of accuracy, in this case, postoperative thrombosis. An AI algorithm is then trained to optimize the network to minimize the risk of postoperative thrombosis. To reduce the risk, the algorithm can change heparin loading dose, give heparin during cardiopulmonary bypass, change protamine dose for heparin reversal, give antithrombin supplement, give blood product, or use modified ultrafiltration. In a simulation of the effectiveness of the algorithm, we observed a relative risk reduction of 40% in predicted rate of postoperative thrombosis through AI-based optimization of management. The next study we will discuss used a novel AI-based method to generate insights from classic epidemiological data. For decades now, we have studied the epidemiology of Kawasaki disease in order to look for clues on its still elusive etiology. The classic approach to epidemiological research involves calculating things such as disease prevalence, seasonality, age, and sex distribution. While this is important data, it is still a reductionist approach which obfuscates a lot of the important information. A few years back, we used an AI algorithm to perform a spatiotemporal scan of cases of Kawasaki disease in Canada over a 10-year period. This algorithm was trained to identify spatial and temporal clusters associated with increased or decreased incidence of Kawasaki disease or coronary artery aneurysm, a rare but serious complication of KD. The analysis identified multiple clusters with both abnormally high and abnormally low incidence, with one particular cluster observed in Toronto, Ontario, between October 2004 and May 2005, being associated with an increased number of patients reporting concomitant symptoms compatible with infectious disease. Moreover, once we understood that insights were hidden within the complex spatiotemporal distribution of Kawasaki disease, we were able to start exploring how the spatiotemporal distribution related to other important factors, such as weather patterns, pollution, and the atmospheric concentration of biological particles, further improving our understanding of the etiology of Kawasaki disease. Finally, we use these findings to create a Bayesian prediction model for local monthly incidence of Kawasaki disease, incorporating spatiotemporal effects, population demographic, weather patterns, pollution, concentration of biological particles in the atmosphere, and the activity of various infectious disease throughout our spatiotemporal matrix. The model showed here in the lower left corner demonstrated excellent concordance between the predicted and observed rate of Kawasaki disease. Interestingly, the model would have predicted a substantial decrease in the incidence of Kawasaki disease with a reduction in infectious disease activity, which was the exact situation observed with the COVID lockdowns, which was associated with a concurrent reduction of both the incidence of many pediatric infectious diseases and Kawasaki disease. This type of modeling substantially improved our understanding of the etiology of Kawasaki disease. We will now turn to another element of complexity that can be addressed by AI algorithm, and that is data complexity. This is a study of the use of cardiopulmonary exercise testing to predict outcomes of patients with heart failure. A standard exercise test includes two components: a measurement of exercise capacity through a maximal exertion test, and a measurement of respiratory function through breath-by-breath analysis. A standard exercise test lasts 10 minutes and generates upward of 100,000 data points, given that multiple measurements are taken with each breath the subject takes. Out of those 100,000 data points, the software attached to the exercise test machine calculates summary indices, which are then considered by clinicians as part of decision making. The subtle variation in breath-by-breath measurements are ignored in summary indices and in conventional risk models. Currently, data from the majority of the submaximal stages of exertion and breath-by-breath data are wasted because of their high level of complexity and unclear prognostic value. However, we hypothesize that using the subtle variation in breath-by-breath measurements could improve our ability to predict outcomes for patients with heart failure. This would not be possible with traditional statistical model, but can be done using machine learning. We use exercise data from 1,156 patients with advanced heart failure, of whom 16% reach end-stage heart failure within 1 year to test this hypothesis. We generated multiple prediction models with various degree of data reduction, starting with the most reduced data consisting of single CPET metrics and scores, then to include exercise stage data, and finally breath-by-breath data, with the latter two groups of models being developed using machine learning. As can be seen here, the models with the most reduced data depicted in black had the worst performance, with a neural network incorporating all breath-by-breath data performing the best. It follows that the simplification of high-resolution information is unnecessary when analytic strategies are used, and this practice may even limit performance of predictive models derived from prognostic tests. The final example that will be discussed today has to do with multisystem inflammatory syndrome in children, a rare but potentially serious complications of COVID. Early in the COVID pandemic, a small number of pediatric patients with a recent COVID diagnosis or contact with infected patients were identified with symptoms of an hyperinflammatory disease, which shared many clinical features with Kawasaki disease. Shown here is the change in clinical feature for 664 patients labeled as having Kawasaki disease early in the pandemic. What you are seeing here are spider plots of various changes in this cohort of patients in the first two waves of the pandemic, including the original strain in the alpha wave in dark blue and delta wave in light blue. The middle axis is the relative change from a control population diagnosed with KD before the COVID pandemic. As evidenced here, during the pandemic, the population of patients labeled as having Kawasaki disease saw many clinical changes. Average values of many biomarkers changed. So did patient management and rate of complications. What this data tells us is that some MIS-C patients are likely being mislabeled as Kawasaki disease, particularly early in the pandemic before MIS-C was fully described. It can also reflect diagnostic confusion, hypervigilance, and overdiagnosis. Since then, clinical diagnostic guidelines for MIS-C have been created, but there is considerable overlap between the guidelines for the diagnosis of MIS-C versus those for Kawasaki disease. So much so that approximately 55% of patients with MIS-C also meet the diagnostic criteria for Kawasaki disease. The implication here is that there is a need for a clinical diagnostic algorithm to help with the differentiation of Kawasaki disease and MIS-C. The question here is how to create such an algorithm when there is no gold standard or definitive diagnostic test for either Kawasaki disease or MIS-C. One option is to use unsupervised machine learning. In unsupervised machine learning, training examples do not need a ground truth label. The model finds undescribed patterns in data by identifying alike observations and organize them in clusters. Those clusters can reveal important facts about the underlying data. This is in contrast to supervised learning, where each training example has a ground truth label and the algorithm learns how to separate examples by their label. To address the problem of differentiating MIS-C from Kawasaki disease, we used a novel machine learning method called Gaussian mixture model. In this three-dimensional model, each patient represents a dot, and the closest two dots are to each other, the more alike these patients are. On the left panel, you can see the patient population with their diagnostic label. That is the diagnosis that was given to the patient by their treating physician. Each patient group is represented by a different color. Patients labeled as MIS-C are in green, those as Kawasaki disease in red, and finally, control patients with COVID but neither MIS-C or Kawasaki disease are labeled in blue. You can see considerable overlap between the three groups, with many MIS-C patients having a profile more compatible with Kawasaki disease, and vice versa. On the right panel, you can see the 5 phenogroups identified through our Gaussian mixture models. Phenogroup can be thought of as clusters. We then use the phenogroup membership to infer diagnosis, with patients in cluster B and D in red and black having Kawasaki disease, those in cluster A and E in green and purple as having MIS-C, and those in cluster C in blue. We were then able to validate this algorithm based on phenogroup membership on a cohort of Kawasaki disease and MIS-C patients with non-overlapping diagnosis, and found an excellent ability to assign patients to the correct group. At this point, I presented examples of how novel artificial intelligence method can help in addressing system complexity in a way that traditional approaches have not been able to before. The next frontier that will need to be addressed is the implementation for AI-based systems, such as those discussed today. It is important to note that less than 1% of AI systems developed for medical use are successfully implemented clinically. Seen here on the right side of the slide is the implementation status of various types of AI applications, with applications in green representing domain with successful examples of implementation, those in orange representing domain where implementation has been done for research only, and red applications are still in development. As evidenced here, the applications addressing the problem with the lowest level of complexity on the left side of the graph are those with the highest rate of successful implementation. Part of the implementation gap has to do with the complexity of the clinical data environment, and addressing this complexity through AI-powered data solutions will be necessary. Addressing this implementation gap is the genesis for the creation of the Cardiovascular Analytic Intelligence Initiative, CVI², at Johns Hopkins University, with a multidisciplinary and comprehensive approach to the development of tools and method to address the inherent complexity of biological and clinical systems. This means developing the data infrastructure for the real-time acquisition, processing, and integration of predictive model in the clinical IT framework, and test new strategy to create clinical prediction model using modern statistical method and machine learning. Finally, evaluate the implementation and outcome of predictive models after they have been deployed as part of patient care. Thank you for your attention, and remember that the next frontier for AI in pediatric cardiac science will be the embrace of complex systems.